In this case, Bernadette wants to fence in a rectangular courtyard. She's going to have three sides, each costing $8 per meter in fence, but one side is a little bit more expensive at $10 per meter. And she knows that she wants to enclose 100 meters squared. She just doesn't know the greatest possible area, so we're going to figure that out for her. Well, we know that area is equal to length times width, which means 100 equals length times width, because we know the area is 100, so L equals 100 over W. Now, we know that the cost of the fence is going to be 10 times one length, plus 8 times the other length, plus 2 of, we're going to take 8 times the width and multiply it by 2, because we have 2 of those widths. So we're going to get 18L plus 16W for the cost, but we can re-express L in terms of W. Since L is 100 over W, we can say that really the cost in terms of W is 1800W to the negative 1 plus 16W. Now the domain is W greater than 0. Theoretically, the width could be virtually 0 and still have an area of 100 meters squared. Or the width could be virtually, virtually any positive number we could imagine, and we would still, it would be possible to have an infinitely small value for L that would give us an area of 100. So basically, for our two endpoints, we're going to have to consider the limit as W goes to 0 and the limit as W goes to infinity. In between, we're going to take the derivative of c with respect to W and set it equal to 0 and solve for W. And that's what happens here. And what we end up with is that W is approximately equal to 10.61. Now, when we take the limit as W goes to 0 of the cost function, we see that this value here would grow without bounds, so the limit would be infinity. If we let W approach infinity, we see that this term here would grow without bounds, so the limit would be infinity. In between, though, if we let W be 10.61 approximately, we get a cost of approximately $339.41, and that is the minimum cost.